The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, well, this is our second presentation. In this presentation, we're going to go over the reactor core and secondary design. We have our preliminary design done with some slight optimization left to do. Basically, we're going to give you the proposed design and some specs on it. Then we're going to go over the core and secondary. Me and Rory are responsible for the core work, and Jess and Robert are responsible for the secondary work. And then we're going to talk about what's coming up next. So as you guys all know, our reactor is a lead-cooled fast reactor with a supercritical CO2 secondary loop. Our initial power guess was actually 750 megawatt thermal, as some of you may have known, but we've revised that upwards to 1,000 megawatt thermal, which with our efficiency is about 450 megawatt electric. Although that's not necessarily electricity we'll be producing, depends on how much of our process heat the process heat folks end up taking from us. But that's our capability of production right there. This is mainly limited by the velocity of our coolant, the LBE. Beyond about 2.5 meters per second, there's a serious degradation and corrosion of the claddings that the LBE comes in contact with. So we are limited to 2.5 meters per second as a result. This is also the subject to change as our delta T and flow area change. We'd like to get it up to 1,200 megawatt thermal because that'll give us roughly 500 megawatt electric with some room for process heat folks to take something. And that's what we'd like to get to. So here's our core. This is what it looks like. It's a hexagonally shaped core with these are each of the fuel assemblies right here in black. In purple are the control rods. In beige is our reflector. In red is our shield. And orange is our coolant. And the little blue outline is our clad. Note that this isn't actually our containment. It's actually bigger than this, but it's just a circular view of the actual core itself. Rory will go into more detail on the materials used and such during his portion of the presentation. And here's our secondary. Here's our full flow mock-up without any values. This is just to give you an idea. We've revised it since we've talked to you all again. We've cut out one of these reheater condenser loops to just to simplify it. So you can kind of see it comes out. We're going to have about 2 flow pass out heat exchangers. We're going to have 2 turbines, each at 250 megawatt electric. So that's why we're trying to get to that 500 number, because we still have some room there that we can produce more power. So I'm going to hand it over to Rory, and he's going to talk about the core design process.
Okay, so we did all the core design work using MCMP. MCMP 5 was the version we used, and to start with, we didn't want to just pick numbers out of the air, so we used primarily the STAR reactor and the European lead-fast reactors to get some first numbers and some original pin and assembly diameters, and those worked pretty well. But as you go in the next slide, you'll see we started iterating on it to see if we can get improvements. The first thing we did was, from the literature and from talking to Dr. Short, we realized that the steel cladding needs a protective layer around it to protect it from erosion by the LBE. And so our fuel design, instead of just going the normal fuel gap clad, it now has to go to adding protective layers anytime we have contact between coolant and steel. We also looked at then control rod positions. Right now we're only doing criticality calculations with MCMP, so it's effectively only beginning of life. But that would be a subsequent step to start doing depletion, but we wanted to get this down first so that we knew we were starting from a good base. And then in the second slide, you can see, so this first iteration, this is our result. This plot shows the source distribution, so a fission source distribution, and you can see that we have a 12-ring core, of which the first 10 rings are fuel. And these are the control bundles, obviously in rings 5, 7, and then you can kind of make out 9 here. But we could see that we were getting a lot of early deaths, and we weren't really reaching the edge of our fuel. And given that we wanted to maintain our power, we didn't want to shrink the core too much. So we, in the second iteration, these are the K effectors we produced with the control rods at different positions. And so the two things we took away from this were that we wanted to wanted to move to zonal enrichment so that we could get fission sources all the way out to the edges of our fuel. And we also wanted better control of the K effective, because you can see that the values jump up a lot towards the end, and that was because we had uniform axial zoning, so that the way the control rod interacted with the model was as you pulled it out towards the top, you got a spike. And so we realized we were going to need less fuel at the top. And so as iteration 2, we started, the basic idea was that in all regions of the core we had, we split it into thirds, and starting with 20% at the bottom, we then reduced it by 5 in each third going up. And that would hopefully reduce the amount of, would give us more control of reactivity as we remove the control rods. And then in the intermediate and outer fuel zones, we had plus 5%. So the inner zone was 20, 15, 10. The intermediate and outer were 25, 20, 15. And we were thinking that would help us maintain our power right the way out. And these are the K effective numbers we got. And as you can see, we get a lot better control towards the end, which was what we were hoping for. And I'll briefly go through the, so MCMP doesn't, because it's the same material, it doesn't print them out in different colors, but these first 4 rings are fuel zone 1, and then rings 5 through 7 are zone 2, and 8 through 10 are zone 3. The MGO was chosen as a reflector based on work done at MIT with fast reactors. It was found to produce good breeding levels, which we don't see here because this is all beginning of life. But it gives good breeding without peaking your power too much at the edge. And then the shielding was chosen just because it's a very good neutron killer. One note is that it looks like there are bundles of fuel around it, but really that's just an artifact of the code. It's just continuous coolant around here. It's not constrained in cladding. Next slide. This is a look at an individual assembly. Again, in the corners here, those lines don't exist. They're just the way MCMP likes you to design universes. And one slight note is that since we made this slides, this isn't 50% and then 25, 25, it's thirds in every region. But you can see how the fuel zone is, each color represents a different type of fuel, and that's how we're zoning. Next slide. And so here you can see the results of those runs. And the good thing we saw is that our source particles are going right the way to the outside. So we're now making full use of our core. This is with the fuel rods a quarter in. And so, sorry, this is an actual picture, figure 2, and this is the control rods a quarter way in. And so we lose power towards the top, but we're getting power right across the breadth of the reactor, and it made us think that this was a good second iteration. And I think we now move, power calculations.
So just to kind of go over what we use to calculate power, some of you may be wondering, we didn't do first we took us a while because we thought we'd be able to get the power out of the code, that the code would more or less say your reactor has X amount of power. That's not true because codes don't really have a time variant in them. They don't consider time. So there's no way to get power out. So we used a basic calorimetric calculation, which is power equals m dot Cp delta T, or m dot is rho VA. As I mentioned before, V was limited at 2.5, and rho is for the LBE is about 10,500. A is the cross-sectional coolant flow area, and Cp is about 150 joules per kilogram Kelvin, and that's the heat capacity. And finally, delta T is the temperature change across the core. So what you get out of this is that this is how our power level could potentially change. It's directly proportional to A and delta T, and those are two factors that we could see changing. Potentially, we think the power level could still go up because we may still get a larger delta T across the core, and we could increase the amount of coolant in the core, and thus increase A. So another calculation we did to determine, because one of the issues with LBE is that after shutdown, it begins to cool down. It can eventually solidify. Its melting point is like 398 Kelvin. So what we wanted to check was how much power, how much decay heat is our reactor producing, and thus how much is our LBE heat is our LBE going to be receiving. After a month of shutdown from a long operation, more or less infinity, it's still producing about 3 megawatt thermal of power. And after a month of shutdown from 1 month of operation, it's still producing about 400 kilowatts. One thing we did this fairly recently. One thing we need to see is like how much power produced is sufficient to keep the LBE liquid, and then work with process heat folks on storing some heat and then using it when we're shut down to keep us warm. We had some issues actually. More I had issues getting the power level to correlate to a temperature rise in the liquid, but we're going to be working on that. So I'm going to turn it over to Robert, and he's going to talk about the secondary system.
So we're going to model our secondary system in ease, which I've already begun to do. This is going to allow us to do much more efficient calculations for each of our parameters: mass flow, temperature, pressure, etc. When we first went through and did the model in ease, we made some initial assumptions, and we neglected some things to make it a little more simplified so we can get a first version out. But as I said, it's going to be very easy to move forward in the future and make changes as we get new data and change parameters to optimize it. You can see our secondary system here with some initial numbers that we've plugged in using ease calculations. Our assumptions that we made at first are 650 degrees out of the reactor core into the primary heat exchangers, as well as their output of 478.8, which is a calculation we did by hand, just as a rough estimate. Coming out in the CO2 loop, we can see 630 degrees Celsius coming out towards the turbine, and going into that we used 200 degrees Celsius. The last assumption we made to begin with was at the bottom after the condenser. We made an assumption of 50 degrees Celsius as a lower limit because the supercriticality threshold for CO2 is about 30 degrees Celsius, so we gave it a little bit of a margin and used that as an initial run through. And so with our initial calculations of temperature drops, we were able to get some values and some generic pressure ranges that we're going to use going forward to keep the CO2 supercritical and make sure that nothing is too out of the ordinary. And we were able to calculate a mass flow for ocean water or river water for the condenser, and that was well within reason, which is a good sign moving forward. We'll be able to be successful in our optimization. And then for the next step with the ease calculations, we're going to need to get more data for supercritical CO2 in terms of enthalpy tables and such, so we can do more in-depth pressure calculations for each parameter at each part of the system. One thing that we actually removed while we were doing these calculations is we had 2 reheaters coming up, and we decided to remove one because we didn't think 2 were necessary at this time. However, other designs we've seen have used 2, and so we need to look further into what kind of advantages that can offer us. And finally, of course, the process heat group will need to use some of our energy, so we need to factor in that and be able to rerun the calculations accounting for everything that they're going to need off of our secondary system. And now I'm going to hand it over to Jess to wrap things up.
I'm just going to go over quickly that we're using a Brayton cycle instead of the traditional Rankine cycle that you'd find in a PWR, BWR. And so this consists of 4 steps. It's typically an isentropic process. Then you have an isobaric process, isotropic, isobaric. So you've got an isentropic expansion, and then it starts with an isentropic compression, and then isobaric heat addition, isentropic, isentropic expansion, and then isobaric heat removal. So initially we were looking at the heat difference heat exchangers, and we were examining what type would be good, so what type would be suitable for this type of thing. And most of the LFRs that we've seen in the literature use in-core heat exchangers. So we were looking at ones that would work with inside the core. And the initial thought process with the LFR and the supercritical CO2 was to use a more compact cycle. So initially we decided that we were going to try to do the printed circuit heat exchangers that are made by Heatrick. It's a British company. And the problem with that is that the friction coefficient for the lead bismuth eutectic is quite large, and it ended up being a little bit of a problem quite a bit of a problem when it came to how well your flow was going to be, your corrosion, etc., and the heat exchange. So ultimately, we actually decided to go with the shell and tube heat exchanger for the in-core reactor. This picture actually just shows the size difference. This is why we initially wanted to go with the PCHE, because it's smaller, it's more compact, less materials, less footprint, kind of like hovers back to our overall goal. Okay, so the PCHE, although we're not going to use the printed circuit heat exchangers inside the core with the initial heat exchanger, we are going to use it for the recuperators that Rob was talking about earlier, recuperate 1 or 2, depending on how things go. And this is a quick diagram of how they work. Effectively, they're plates with like coolant flowing in different directions, and they have semicircular channels that are on the different plates. One fluid flows one direction, the other one flows the other. For this, in these heat exchangers, it's going to be supercritical CO2, so on both directions. So we don't have to worry about the different sizes. With the lead bismuth eutectic, we had to worry about having a larger channel size, like diameter, to ensure that the flow was appropriate. Actually, can you go back? I'm sorry. Yeah, so that has a competitive efficiency, compact design, and what I mentioned earlier, the friction factor becomes an obstacle. Thanks. So the standard shell and tube heat exchanger is a pretty simple design to make. It's a low cost. We went with a straight tube heat exchanger because it is simple to make, it's low cost. You don't have to worry about too many things. It has been done. It's considerably larger, as you saw in the previous slide, but it does still have a very competitive efficiency with the PCHE. Additionally, we chose, the picture did not come out here, but we're choosing to use instead of a square aligned geometry, we're going to go with a triangular geometry so that the flow through the tubes, like lead bismuth flow through the tubes will be, or through the tube. I'm sorry the picture didn't show up, but maybe if I draw it here. So it's going to, instead of being, it's more like this rather than like this. Oops, excuse me. So that when the lead flows through the subchannels, it has a better flow. So going forward in the next step, the secondary cycle is we're looking at getting better data, more accurate values, and really trying to optimize what we have going forward. Re-examining what Rob was talking about earlier, the reheater, the compressor, what we need for that, as well as the process heat removal. And then also we're looking at other situations that might involve if the hydrogen plant is down or something like that. And then the core is also going to be looking at natural circulation, decay heat work, as Brayton was talking about earlier, and continuing to optimize the core zoning, thermal fuel analysis. So, any questions?
I noticed at least the first iteration for your secondary loop had a mass flow rate of about 1,400. Is that, I think we were under the impression that that could be varied depending on how much power we need to take out. Is that true?
Right. So our
Supercritical CO2. Yeah.
so on the you guys obviously can take all of that if you wanted to. Our objective was to be able to produce at least 100 megawatt, be able to produce at least 100 megawatt electric, which we can. So it's now, so if hydrogen and biofuels need that amount of processing, you guys can basically take all of it. It is subject to variance as like we increase the power level of the reactor, it's going to increase that mass flow rate. I actually think it might be slightly higher than that now. Last night we had that's why the power level changed when we did some like recalculating and decision making. I think that mass flow rate's actually going to go up.
Anyone else? Tyrell, do you have any questions?
Yeah, I have a few here. Do you guys know what the proliferation limit is for uranium enrichment?
So we're trying to, originally LEU is like 20%. So we know we can kind of stay at like 20%. Right now, radially, we have some 25%. And we weren't exactly terribly excited about doing that because we knew it's no longer LEU, it's like more medium enriched. Mm-hmm. But given its advantages, we may stick with it. We know like other designs have used like more highly enriched uranium, and like a lot of the ones we based off kind of stuck to that 20% enriched limit. But we think with like better zoning, we can still, because like with the 20% straight through, we had plenty of reactivity to work with. It was just like trying to get it a flatter like flux profile to like, which is what we want. You don't want to like a straight peaking in the center. So we think that if we can stick with low enriched uranium, that would be really ideal. But it's going to take some like fancy fancy zoning. But at the same time, you run into like design limitations. Like you can't have like 10 axial zones. Your manufacturer will go nuts. So.
Right.
Just quickly, one way we were thinking we might be able to cheat there as well is because we have the reflector right at that region. While we could start with less than 20%, from previous work with SFRs using this kind of layout, they've had rapidly produced a lot of Pu-239, and so we could, that could balance it out. And so, in the relatively maybe within 100 or 200 days, we could get to 25% equivalent enrichment, which would allow us to get back to this nice power shape.
Yeah, I think our depletion calculation is going to really shine a whole bunch of light, because once we do our depletion, if it ends up we're adding a ton of reactivity very quickly, then we're going to have to kill our reactivity at BOL. So hence we're going to drop our enrichment.
Okay.
So
BOL being
beginning of
Okay. Another question is, do you only have coolant flowing around the outside of the core?
So it's hard. So it's that core that picture's like it doesn't have the I guess the resolution.
The assembly diagram, you saw so all orange here is coolant, and then there's a gap between every assembly, and then there's a gap on the whole core.
Right, so the red is your fuel.
Sorry, red is fuel, and then I don't know why I didn't show it, but there's then LBE filled gap, and then protective layer, clad protective layer, and then coolant again, and then the same around each assembly.
Yeah, you can't see it in here because I think it's just resolution. I feel like if you actually get like super close, and MCMP doesn't produce color, that's us adding it. So.
Okay. Yeah, I just wanted to make sure you guys weren't pumping all the heat out around forever. And then you had T91 on there. Is that stainless steel? Is that...
Yeah, so it's actually Dr. Short's work. We went basically from his PhD thesis, and we have that protective layer and that like inner layer of T91.
Okay.
But yeah.
All right. That's all I got.
So you did mention you're going to be doing depletion calculations to look at what happens at the end of life. How are you guys going to be doing that?
So probably making a couple first runs at it using M-code, but also in the process of rewriting the model in Aranos, which is a deterministic fast reactor code. And that'll be really useful. Well, from my experience, it's a very useful code because it gives you your void coefficient, your temperature coefficient, your beta, your K. No, beta is the one I was thinking of, and a lot of your different kinetics. So we could have a long list of all our safety concerns or safety positives, and that will also, you know, a 2-hour run can give you as much depletion as you want.
Yeah, that's kind of our limiting factor in depletion. MCMP takes a long time to deplete because it's a Monte Carlo code.
Yeah, that makes sense. Well, then I have a question for the secondary side folks as well. Usually when you worry about a loss of load in a reactor, you only have one load, it's the grid. But in this case, you guys have two loads of the same magnitude, electricity as well as process heat. Have you guys looked at what to do in the event that just one of them goes down? Will you have to lower the power produced, or would you be able to send the rest of that either electricity or process heat to the other process and keep things going?
Right, I mean, we're still in the stages of setting up the E system so that we can do these calculations a lot faster, and that's certainly something that we are looking forward to analyzing. When we consider if the power goes down, it'll be very simple to try and reroute and see where things need to be, where things need to go. But yeah, it's definitely, as I said, we're just setting up the initial ease calculations, and the more in-depth optimization and crisis analysis, the risk analysis will be done in the next steps.
I think one thing is, because right now we have 2 turbines which can produce 500 megawatt electric. So in the case that hydrogen or biofuel goes down, we'll probably have the capability to like flow that much through the turbines and stuff, because that's what we're going off right now, and then they're going to take theirs off as well.
So you won't be running the turbines at their rated capacity or anywhere near.
Right, and once we know how much is being taken, if like, for instance, like if it's half of it's taken roughly, maybe we just shut one turbine down, have one running full time, and if like they lose their thing, we can just close the valve to process heat, open the valve to the turbines, and fire them up and let's go. So.
Okay.
Especially because the turbines are not very large in terms of like pricing and whatnot. If it turns out that they take so much that we don't really need a second loop during like full power operation, assuming they're going, it's so small, it shouldn't matter that much in terms of space and whatnot.
It wasn't like have an extra turbine lying around. That's unfortunate because of the size and the cost. It works pretty well for us.
Oh, good. That's because of the CO2. Awesome. And then, have you guys looked into any specialized safety systems that you'd need for an LFR, as opposed to what sort of safety stuff might be different from a light water reactor?
One thing we're definitely looking at is, as I mentioned, is a natural circulation would be really ideal. That analysis is going to happen in the next step, and we can determine like how close we are to a natural circulation. Obviously, that's a fantastic safety feature to have. In general, the LFR has a lot of like passive safety features that just like it's got a better heat sink than it's got a better room to boiling of the coolant and all that. So it's got a lot of passive safety features. But I think there's going to be some work on like a more active safety. I mean, our rods will be like scrammable. We'll have to do some like. I was thinking about this earlier, just kind of on my own. I was like, well, with lead being as thick and dense as it is, how easy is it going to be to scram a rod through it, and displace the lead? So there's some like consideration to be done with all that, but some of that stuff is just limited by, I don't know how we're going to be able to check to see if our rods will actually be able to scram fast. I imagine they have from experience, so. But.
Okay, well, does anyone else have any questions? If not, then I'd like to thank the core team. That was quite good.